Corrosion Part 8. Hello everyone, welcome to Corrosion Audio Lecture 8, in which we will look at corrosion protection. In the course so far, we've looked at algebra of electrochemical corrosion, the thermodynamics and kinetics to predict if corrosion happens and how fast, and we've looked at real-world phenomena which can happen when those predicted corrosion processes take place. The real-world phenomena obviously being a bit more complicated than the idealized models. What we now can get to, finally, is the useful engineering practice of corrosion protection, how to stop the real-world corrosion phenomena, either by looking at the idealized thermodynamics and kinetics and asking how to prevent or slow down the corrosion, or by looking at the real-world phenomena and thinking about how those might be avoided. This audio lecture will cover Chapter 5 in the lecture notes, the Chapter 6 on high temperature corrosion, which really refers to corrosion of metals in furnaces, or oxidation of metals used as high temperature heating elements. That chapter I will leave for bonus material. So I leave it for the end of the lecture course when I give the course live, and in this audio lecture course I'm going to leave it as bonus material, which I will only produce if there's some demand for it. You can read about it in the handout, but it's very different from the electrochemical corrosion processes which make up chapters 1 to 5 and which are the main focus of interest for the corrosion course. Okay, by way of introducing the idea that corrosion protection is very important in modern engineering, here's a quote from the film Star Trek Into Darkness. Now, I don't know why I use this film quote. I didn't particularly enjoy the film compared with the classic series or the classic films. Nonetheless, although the lens flare in Into Darkness was pretty annoying, it did have this particular spectacular scene, needlessly spectacular, but spectacular nonetheless, of the Starship Enterprise arising up out of a saltwater ocean, and the chief engineer complaining that there was really no good reason for having hidden the Enterprise underwater. After all, this is a ridiculous idea. It's a ship designed to travel in space, and it's a completely dumb idea to hide it in the ocean, because that saltwater is certain to corrode the... And then the quote was cut off because of the frenetic pacing of the film. You can imagine the salt water was going to damage the metalwork on the outside of the starship, and Montgomery Scott was rightly complaining about this situation. If you know the characters in the show, you might realize that Montgomery Scott complains quite often and sometimes needlessly, and you might get the impression that he could have been complaining needlessly in this case too, because after all, as a feat of modern engineering, or even future engineering for us, surely the Starship Enterprise has sophisticated corrosion protection mechanisms of some sort. Or you might even think I'm making a big meal out of this, because surely the Starship Enterprise is built from some sort of extremely strong metal, maybe a very passive metal like titanium, and therefore it's probably fine against corrosion, even in salt water. But you might think that, but I say you'd be wrong, because if you had watched the earlier trailer for the first film in the remade series, then you might have seen the Enterprise being constructed in some sort of pretty old-fashioned yard. And some guy looked up from welding together some panels on the outside of the ship, looked up, removed his greasy welding goggles, and then the camera panned out to show the ship. Now, if you know quite a bit about metallurgy, this would confirm to you that actually the outside of the ship is probably made of steel, and then it is going to have these corrosion problems that I tell you it will have in salt water. Now, how do you know it's made of steel? Well, because steel is the main thing that I'd expect people to be welding, and especially with the low-tech welding tools this guy was using in the trailer, he couldn't have been welding titanium. You might know that titanium can't actually be welded under air because it catches fire, and in fact it's one of the few metals which can't even be welded under nitrogen as a barrier gas, because it catches fire in nitrogen as well. You have to weld it under argon. and even then it's not a particularly nice material to weld. So I say from this trailer that Enterprise is made of essentially steel, even if they give it a fancier name, and so it would need not just corrosion protection by virtue of being a passive or even noble metal. Instead it would need corrosion protection of some sort of actively engineered variety, which is what I want to look at in this audio lecture. Okay, Chapter 5 on page 12 of the second handout talks about corrosion protection. One thing we can already do from our Chapter 2 knowledge on thermodynamics is that if I want to design something, I can make use of material selection to make sure it doesn't corrode, because I can measure the local pH, find out what the surface potential will be on the object, and I can choose, using the pH potential diagrams, a material that will be passive against corrosion or immune from corrosion at those conditions. But as well as material selection, there are several things that we can do even if we have chosen, for some reason, a vulnerable metal that we expect to actively corrode at an unacceptable rate. And these countermeasures for corrosion in this chapter I want to split into three different types. I want to talk about thermodynamic methods based on Chapter 2. These are also called electrochemical methods, and they involve making a metal behave in a way that's passive against corrosion or immune from corrosion, even though its natural condition, if we did no special engineering, would be to corrode actively at an unacceptable rate. The second possible thing we can do is we can use kinetic methods, or these we're going to talk about corrosion inhibitors, which will say, okay, I've got a metal which is corroding actively. I don't mind as long as I can slow down the active corrosion to an acceptable rate, so the surface lifetime is acceptably long. We can also talk about doing something called environment modification to slow down corrosion rates. The third category of corrosion protection methods I want to look at are coatings. Now, coatings are a real-world engineering solution, and as such they don't fit so neatly into idealized scientific categories in the way that thermodynamic methods and kinetic methods do, because coatings actually do several things. They can incorporate both thermodynamic and kinetic control methods, as well as something special but fairly obvious to coatings, which is they provide a barrier that prevents the environment from contacting the metal and hence stops electrochemical corrosion, at least until the coating is compromised. Section 5.1 on sacrificial anodes talks about basically bimetallic corrosion. In chapters 3 and 4, we already looked at the algebra for bimetallic corrosion, which explained why, when two different metals are in contact and in a corrosive environment, the more reactive metal really suffers badly and can corrode much faster. The sacrificial anode concept is simply the flip side of bimetallic corrosion, because when we add this reactive metal, which oxidizes faster, we also slow down the oxidation rate of the other metal. So the other metal is protected by a sacrificial anode. Following the algebraic methods we looked at in section 4.1, we can work out whether the protected metal is expected to become simply less active and to corrode more slowly, or even to become immune from corrosion. Which happens will depend on the kinetic parameters of both metals, the exchange current density, equilibrium potentials, etc., and the areas of the two metals. So that's some work you might have to do. Anyway, what are common choices of sacrificial anodes? The answer: zinc, magnesium, sometimes aluminium alloys. And what are we looking for in a sacrificial anode? Well, it needs to be a metal which is more active than the metal to be protected. So any of the reactive metals, zinc, magnesium, etc., satisfy that criterion. Some reactive metals can't be used as sacrificial anodes. Titanium is reactive, but it's also spectacularly passive, and your titanium if bolted onto some other metal, the titanium would simply form a passive titanium dioxide surface film, and thereafter it would be close to inert, and it would provide no protection. What you need in your sacrificial anode is that the reactive metal does undergo continuous active corrosion or dissolution, because it's precisely that process which moves the surface of the two-metal system to a potential which is less corrosive for the protected metal. Okay, so it's very common to use sacrificial anodes at sea, on oil rigs, on the sides of boats, maybe sometimes inside domestic hot water tanks. There's not too many things you can do wrong with a sacrificial anode. It needs to be installed. They may need to be replaced occasionally if they aren't designed to last for the whole service lifetime of the thing to be protected. Mainly, one of the more amusing things that you can do wrong with them, though, is that somebody can come along and they can see this poor suffering sacrificial anode which is dissolving away, and they can think, this part of the exposed metalwork seems to be the only really badly corroding part of the structure. So what I think I will do to improve the situation is I will come and I'll apply some corrosion protection. Well, but we only need to be applying corrosion protection to this bit. So I'll paint over the sacrificial anode, these people say. And when they do that, of course, this removes the useful corrosion protection which it was providing, and in that case the rest of your structure is no longer protected. So sometimes you can find sacrificial anodes with this helpful instruction stamped into them deeply so that it survives a good deal of corrosion. You can find the helpful instruction, do not paint, in which case please don't. Section 5.1.1 talks about typical questions or calculations which you might have to do involving sacrificial anodes. You might get some manufacturer data about the components, the individual sacrificial anode. You might have to use that data to calculate how many sacrificial anodes are required to protect a certain surface area of metal, say on an oil rig. You might need to calculate maybe the spacing between the sacrificial anodes that is produced by this. You might have to select dimensions of sacrificial anodes, find out how much of the mass of the anodes is left after some period of time. One of the parameters you might calculate with then is this wastage rate of the anode material, which is kilograms per ampere. So how many kilograms of the anode, which might be an alloy, is lost for every ampere of corrosion current which it soaks up from the structure. You might also have to calculate how long it is before the remaining surface area of some sacrificial anodes is too small to provide the required amount of protection, hence how often do they need to be replaced. One final thing to remember as a comment is that when sacrificial anodes are used, they do cause the surface potential of your two-metal system to change, and the surface potential probably changes to a value where the hydrogen evolution current in most situations will be much faster than it was without the sacrificial anodes. This means that when we talked about hydrogen embrittlement as a corrosion mechanism, that can actually possibly be made worse by sacrificial anodes. It's more likely to be made worse by a powered system which applies a larger change in surface potential than is typically exerted by sacrificial anodes, but they can cause hydrogen embrittlement. Section 5.2 on page 13 is where we get to when we say that we do want to do something more high-tech than using a sacrificial anode, which seems like a bit of an early 20th century solution to us. We can say that since we are in the 21st century, we don't want to go to the bother of changing sacrificial anodes when they wear out. Instead, we can use an electrical power source to provide the same service, because all we need to do is change the surface potential of the metal object so that the metal to be protected corrodes more slowly. And we can do that with a power source in a system called an impressed current corrosion protection system, or ICCP. on page 14, if we want to use an ICCP system to provide cathodic protection, the same kind of protection which is provided by a sacrificial anode, then we might have these diagrams to explain what's going on. So looking at the pH potential diagram or Pourbaix diagram, we might know that if we have a block of iron or steel, we might have spontaneous corrosion at some indicated condition. We find out the pH and we measure the surface potential, and we see that active corrosion of the iron is expected at some troublesomely fast rate. In the Evans diagram for kinetics, we can find out what that corrosion rate is. We're just looking for the intersection of the lines for the anodic and the cathodic reactions as before, and the spontaneous corrosion current density is going to tell us that log base 10 of this corrosion current density is about -2 in whatever units we're thinking about, maybe amps per square meter, and maybe this is unacceptably fast. So what can we do about that? Well, pretty easily, with an ICCP system, we can apply a new potential to the surface of the metal. So we can apply some EICCP by some sort of powered electronic system, and this has the effect in the pH potential diagram of moving our situation close to the border between ion immunity from corrosion and active corrosion. Now, suppose we can do that. We now find on the Evans diagram that we have a lower surface potential, which means that when we look up the current densities for the two processes, we see that the corrosion current density for the iron has decreased by a couple of orders of magnitude. So that's excellent. The iron is now going to be actively corroding, but barely, only at a very slow rate. The cost of that is that the hydrogen reaction, the hydrogen evolution on the iron surface, is now proceeding at quite a fast rate, and the currents no longer balance. The anode current density is no longer of the same size as the cathode current density, because there's much more of the cathodic hydrogen evolution happening. Therefore, the cost of providing this ICCP corrosion protection is we have to apply current, and supplying current to balance these processes costs us money. Well, it costs us electricity, which costs us money. This means there are some comments we can immediately make about the best way to operate a cathodic protection system like this. A comment is that we should be looking to decrease the surface potential of the metal to be protected, in this case the iron, maybe close to the boundary between immunity and the start of active corrosion. That means there's going to be pretty negligible rate of corrosion. We might even want to try and push the metal just slightly into the immune regime so that there's basically no corrosion. But we wouldn't want to push the potential to any more negative a value, because any more negative surface potential provides no further slowing down of the iron corrosion, but it does continue to provide an increase in the rate of hydrogen evolution from the unbalanced cathode process. And that would simply increase the amount of electricity we need to supply and increase the cost of operating the system without providing better corrosion protection to the iron. In fact, it would even be potentially worse, because if we have a larger amount of hydrogen being evolved, we have a greater risk of hydrogen embrittlement taking place. And that's something which we can easily cause to happen by accident with an impressed current corrosion protection system. Now, we also want to know, what does the schematic of the electronics for an ICCP system look like? And we have this quick sketch here. This shows that you have your metal being protected, a power source, and strapped to the power source, importantly, we have a driven anode. This is important because what I said so far is we're supplying an electron flow to the metal to be protected. That's to supply the net cathode process that takes place on the metal because of the accelerated, unbalanced hydrogen evolution reaction. That net cathode on the protected metal needs to be balanced by a driven anode somewhere else, and here's an important question: what is a driven anode? Well, if we have something like an oil rig or a ship, the driven anode could simply be an electrolytic process happening in the ocean water next to the metal which is being protected, the ship's hull. We could have in those cases something like a platinum mesh, a nice good electrocatalyst, and we could, with our power source, we could be driving this to a surface potential where the anode process takes place. If this was in fresh water, then an anode process might be oxygen evolution. In seawater, a process which happens more readily, and therefore instead of oxygen evolution, is chlorine production. This means we potentially need to be careful and avoid using ICCP in seawater if you're concerned about producing chlorine and you're worried about the fumes from that. Alternatively, we might not want to just use the electrolysis of the nearby water to provide the driven anode. We could instead use a consumable driven anode. This is fairly common. We might have a load of scrap iron, some sort of iron that's been condemned. We could simply strap that to the driven anode connection of our ICCP system, and the driven anode, it's forced to undergo by the applied current an anode process, and that's probably going to be the dissolution of the scrap iron. But that's okay, because we don't really care about the scrap iron. Okay, let's talk about advantages and disadvantages of the ICCP system. So a big advantage compared to sacrificial anodes is we don't need to find them and replace them. If we have, say, a buried pipeline, that's a very big advantage, because accessing the actual pipeline itself to replace sacrificial anodes could be difficult. Whereas if we have a driven anode which is simply connected by wiring to the pipeline at a few fixed positions, but the wiring connections are not going to degrade, then it's going to be easier for us to get at the driven anode to service that if we need to. Another advantage of ICCP is that we're talking about modern electronic engineering, so we have potentially much more precise control and monitoring of what we're doing. When we had the sacrificial anode, we're leaving things a bit haphazardly. We're saying, okay, well, the zinc's quite reactive. I will happily balance that off with some quantity of iron. But as the surface area of exposed iron changes over time, for example, as paint wears out and so more iron is exposed during the lifetime of an oil rig, we might find that the applied surface potential varies from what we initially set it to, and we don't have very good control over the protection provided by sacrificial anodes. If we are using modern electronics to apply a surface potential, we can pretty reliably control its surface potential to be what we want it to be. So this all comes with some costs. ICCP is a more complex system than a sacrificial anode. We can have power cuts which could affect it. We can have simply more components involved, so we might have to worry about corrosion of electrical contacts and then the system fails, even though the power source is fine. We might worry if, for example, our driven anode is some scrap iron and corrosion near its connections causes it to fall off the system, then probably the ability to drive anode current is going to fail. All sorts of electronic engineering things can go wrong. One of the more frightening possibilities that can go wrong with ICCP is that, unlike with a sacrificial anode, which you just bolt to the side of the system you want to protect, it is possible to completely mess up with an ICCP system. You could connect the electrodes the wrong way round. People have done this in the past, and you might find then that your thing to be protected, which you meant to make into a cathode, has been accidentally connected as a driven anode, and it's actually being destroyed by a improperly installed ICCP system. So it needs qualified and fairly skilled installation. Your ICCP, it also comes with some costs, the cost of money for your electrical power supply. And then we have what's coming up in section 5.2.1, the phenomenon of stray current corrosion, which can actually be caused to non-protected systems which are near to a system which is protected by an ICCP system. So, section 5.2.1, stray current corrosion. This section shows a quick sketch of a protected pipeline which has been made into a cathode. It's a net cathode because it's driven by the power supply of the ICCP system. In order for it to be a net cathode, electronic current supplying the electron flow for that net cathode reaction is drawn along the pipe by the power supply. But this is a potential problem not for the protected pipeline, but for other nearby bits of metalwork in the ground, because the current being pulled along the pipeline is being pulled by an applied electric field. And that electric field doesn't mind if it's pulling electric current from along the protective pipeline or from a nearby object. Therefore, if you have a nearby non-protected pipeline in the ground, you may find that the ICCP system pulls some stray current from the non-protected pipeline. And that doesn't matter along most of the length of the non-protected pipeline, because that just involves electron flow along its length, but you have this unfortunate point where you have a jump from electron current to ion current through the ground. And remember, the protected pipeline is a net cathode, so the stray current as it jumps the gap from the non-protected pipeline does so by forming a net anode on the non-protected pipeline. In other words, you cause intense localized corrosion at the points where the non-protected pipeline passes in the ground near to the protected one. This kind of stray current corrosion is a major problem which can be caused by powered corrosion protection systems doing cathodic protection. If the environment, if the local, say the ground in which these pipes are buried, is a busy environment, but this is often the case in cities or industrial plants, precisely the places where you use ICCP systems. These are the places where there is actually a risk of there being other infrastructure in the ground which might be destroyed by an ICCP system. So what can we do about that? Well, a couple of countermeasures. First of all, we need maybe to have a detailed knowledge of what's in the ground. And if we're thinking of protecting one pipeline, it might be that we have to use the system to protect all of the pipelines, so that the protected one can't destroy some of the non-protected ones. Alternatively, we should be careful about not using excessively large protective voltages. We only want to use enough to just protect the pipeline we're concerned about. Okay, I talked in Lecture 1 about the range of accidents or disasters caused by failures of corrosion engineering. And these pictures of the Guadalajara sewer explosion in Mexico are an illustration of just how bad a corrosion failure can be. So this in fact was a failure of precisely the kind of stray current corrosion that I have just described. And let me then tell you the story of what happened, or what is thought to have happened based on the investigation. There are some references which I'll put in the caption below the video, and they're in the slide. This is where I get this information from. So we have here on the right hand photograph two pipes. Both of them have a hole in them, and how this came about is by a complex process. Now the pipes are laid out here in contact, but in the underground environment they were not quite touching. You have the larger diameter pipe shown on the bottom. That's a petrol pipeline, and that was installed nearby to the smaller pipe, which is a high pressure water pipeline. Now the petrol pipeline was very sensibly and prudently protected by an ICCP system. It was providing cathodic protection, so the petrol pipeline, as installed, was well protected against corrosion. The water pipeline, meanwhile, was, I believe, galvanized, so it had a certain amount of protection from corrosion. However, this system suffered from stray current corrosion. The ICCP system caused an anode to form on the water pipeline immediately where they were closest, and the anode on the water pipeline overwhelmed the capacity of the galvanization to protect it. So after some time, the zinc in the area was worn out, and the water pipeline began to dissolve through, leaving this characteristic, very concentrated, large hole, which is often formed by stray current corrosion. So this large hole in a high-pressure water pipeline then produced a jet of water, which you can see blasted over the petrol pipeline. And so in turn, the petrol pipeline was worn away, probably by a combination of the jet, its erosive action, and the corrosion caused by the water getting onto the petrol pipeline. Okay, so then you have the very serious problem that you have a hole worn also in the petrol pipeline, which allowed the sewer to fill with petrol, and then sometime later the petrol fumes accumulated in the sewer ignited and caused this explosion, producing a trench up to about 6 meters deep and about 2 kilometers long, and causing a great deal of destruction. So this problem came about because of a quite common in safety failures, a complex chain of failures within which a absolutely key step was a failure to account for stray current corrosion caused by cathodic protection systems. So this is in large part why the installation of cathodic protection systems is a skilled job which requires considerable care for the where it's being installed. It is in fact because of the risks of this kind of failure caused by cathodic protection systems that one of the biggest advances in corrosion engineering in recent decades has been the adoption of anodic protection as a method to prevent corrosion of iron and steel components. So anodic protection is in section 5.3 on page 15. We have the useful observation that when we looked at the pH potential diagram for iron, we saw that it was one of the metals which actually becomes passive in a very strong oxidizing environment. Iron, for example, is passive in concentrated nitric acid. That's potentially a risky thing to do, to store concentrated nitric acid inside iron containers, but it could potentially be done because the iron should remain passive against corrosion in the strongly oxidizing acid. Anodic protection looks at this aspect of the pH potential diagram, that is, for iron and some of the other transition metals, the fact that they have a higher solid oxide which provides passivity in highly oxidizing environments, and it says that we can exploit this using a powered corrosion protection system. If we apply not a more cathodic potential, which we did previously, but if we actually deliberately apply a moderately strong oxidizing potential to the surface of the iron. So the sketch for what we're doing looks very similar. We could draw it on the same diagram you have on page 14. We had the initial idea that spontaneous corrosion of iron is expected to happen. Suppose this is for a pipeline. But if we now use our powered corrosion protection system to change the surface potential of the iron pipeline and make it more positive, we can actually move it into the passive regime. So we're actually making the iron more anodic. This actually has some quite striking advantages, which is because we now have an anodic protection system where the protected iron is passive and anodic instead of borderline immune from corrosion where it would have been a large net cathode. This means anodic protection is potentially much cheaper than applying cathodic protection because we don't have to supply the large current required to balance out the hydrogen evolution which we had on the cathodic protection system. The second advantage of the anodic protection system is that because our protected pipeline is forced to become an anode, there is no possibility of the nearby pipelines being affected by stray current. They can't be made into an anode. I guess there's a tiny possibility they might be made into a forced cathode, but that would be protective for them, so that's not going to be a problem. So the anodic protection, where possible, is not going to cause stray current corrosion problems in the same way, so it can be safer to apply in a complex underground environment. Nonetheless, anodic corrosion protection is a more recent system, and it does have some complexities and risks that we need to worry about. First of all, it only works for metals like iron, which have a higher oxide that allows them to become passive. Okay, but because it works for iron and steel, that means it's incredibly important in practice, because lots of pipelines are made of precisely those things. Second, as well as a somewhat restricted material selection choice for anodic protection to work, we also have the possibility that there is some risk here. Because we're deliberately applying a positive surface potential, so long as the metal remains in an environment with, say, a pH and a low chloride level which is compatible with the material staying passive, then anodic protection will indeed make it passive. But if we have some environmental shift, for example, the pH becomes a lot more acid in the case of iron, then our applied positive potential might, instead of be one that causes passivity, it might actually cause severe active corrosion. Now that's a problem that is partly mitigated with modern electronics because we can monitor what anodic current is being supplied to the metal, and what should be being supplied is a very small current to drive the repassivation of any of the metal which becomes scratched and needs an anode current to repassivate it. If we're supplying therefore a large current suddenly, we can suspect that there is active corrosion going on, and then the system might shut down so that it doesn't extensively damage the thing that's being protected. But there is this complexity. Okay, now if we go on to page 16 with section 5.4 on inhibitors, then when we get here, we'll have finished talking about thermodynamic methods of corrosion protection. So we've now finished talking about simply using engineering techniques to make a metal immune from corrosion, or nearly immune, or passive against corrosion. Instead, in this section on inhibitors, we're going to look at kinetic methods of preventing corrosion, in which we're going to say it's okay if my metal object is corroding actively, so long as I can use a different kind of technique to slow down how fast it corrodes so that it easily lives out its service lifetime. Now, there are various different ways to do this, and they are based on the insights from Chapter 3 on the kinetics of electrochemical corrosion. The absolute key thing to remember here was that electrochemical corrosion involves an oxidizing agent, that's a cathode reaction, and the metal undergoing oxidation, that's the anode. Inhibitors can successfully slow down overall corrosion if either one of those mechanisms can be slowed down and made rate limiting, because they happen in series. So then, let's talk about slowing down the cathode reaction first in section 5.4.1 on cathode inhibitors. Now, we have here an Evans diagram, and if you look at the intersection of the black line, this is the iron dissolution reaction, that's an anode, and consider first spontaneous corrosion, where we look at the intersection of the iron dissolving anode with the hydrogen cathode taking place on iron spontaneously. If we find the intersection of those two lines, we find the current density for corrosion, and if we want it, also the mixed surface potential. If I can do something to my metal to change the exchange current density for the hydrogen reaction and make it smaller, in other words, if I can somehow add an electrocatalyst poison, then I can find this situation of the second intersection where I have this intersection of the iron dissolution anode with the red line, the inhibited cathode. By decreasing the exchange current density for the hydrogen reaction, I have slowed down overall corrosion rate, I've inhibited corrosion. A classic way of doing this is that I can do something really nasty. I can add dissolved arsenic 3+ ions into the water. This is something I can only do sometimes. Inhibitors like arsenic are suitable for recirculated water systems like central heating systems or cooling loops in a plant. It's not suitable for adding to an open water system because many corrosion inhibitors like arsenic, and I've deliberately chosen to show arsenic here to labour the point, quite a few corrosion inhibitors are toxic or bad for the environment. Nonetheless, they are often very suitable for adding to recirculated water systems that are sealed. The way arsenic ions work as an electrocatalyst poison is that they're actually relatively easily plated out of solution. So it's analogous to the situation where I described for copper causing deposition corrosion when it ends up on aluminium, but the situation here is that some arsenic ions are plating out onto, say, the inside of a steel pipe or something, and then they simply poison the hydrogen evolution reaction, and then they therefore slow down the overall rate of the corrosion reaction that can take place. So unlike deposition corrosion, this addition of a corrosion inhibitor causes plating, which is actually very beneficial from a corrosion point of view because it slows down overall corrosion. That's the arsenic example as a cathode inhibitor for the hydrogen reaction. So that's when the relevant cathode reaction or oxidizing agent is dissolved hydrogen ions in water. We have a different kind of inhibitor that we'd consider if our oxidizing agent is dissolved oxygen. The reason for that is that we recall dissolved oxygen very often causes corrosion at a rate that is diffusion limited. And so changing the exchange current density by decreasing it with some sort of electrocatalyst poison often won't actually decrease the rate limiting step when we have corrosion caused by dissolved oxygen, because the kinetics will still be sufficient to cause all of the oxygen reaching a metal surface to react with it and cause corrosion. So if instead we have a situation of oxygen and we want to slow down the rate of this dissolved oxygen causing corrosion, then the best way to do that is to slow down the diffusion limited rate at which the oxygen is supplied to the metal surface. Of course, you can do that by removing oxygen from solution so that it's low concentration, hence low diffusion limited supply rate. One of the more interesting ways of doing this to cut down the diffusion limited rate of oxygen supply is actually to operate in a system which fills up with lime scale. Or we can deliberately cause lime scale to build up on the inside of some water pipes if we were to make them mildly alkaline solutions containing zinc or magnesium ions. Then we'd end up with a thin hydroxide scale on the inside of the pipe, and this solid scale would create a very nice diffusion barrier that slows down oxygen reaching the metal and slows down overall corrosion. Finally, if we don't like the sound of that kind of inhibitor because we think it might create too thick scales, then we can talk about as well adsorption type inhibitors. These are normally organic compounds, often fairly unpleasantly toxic ones, kinds of organic amines, and these are organic molecules which adsorb onto a metal surface, and they create a mass transport barrier which slows down the rate of the cathode reaction by blocking mass transport of the oxidizing agent to the metal surface. Okay, those were cathode inhibitors. In section 5.4.2 on page 17, we can also talk about anode inhibitors. In this case, we're talking about slowing down the rate of the anode half reaction in a corrosion process. So these things are typically said to work by making the metal surface become passive. For example, some corrosion problems might happen, and this is an exotic one, simply because passivity breaks down on my metal surface. A striking example of this is titanium when it's used for handling crude oil, which actually turns out, unfortunately, to be chemically dry crude oil containing no water but containing methanol. In this case, the normal situation of titanium breaks down because we'd normally expect titanium to have a titanium dioxide surface providing very strong passivity against corrosion. But in the complete absence of water, passivity cannot regenerate on your titanium, which means that once the oxide film becomes scratched off, you have reactive titanium metal, which actually undergoes an unfortunate reaction with pure methanol, and the metal will break down. In this sort of situation, we can talk about an anode inhibitor. We can talk about deliberately adding water to what would otherwise be an anhydrous stream of crude oil. The presence of water then provides the ability of metals like titanium, and this also applies to stainless steels in some situation, to reform their passive oxide surface. In this case, I've provided anode inhibition. I've slowed down the rate of corrosion by making sure that the metal is behaving in the passive way that you expect it to behave. Another way, and this is sort of called an anode inhibitor as well, is that you might add chromate solutions. You might spike those into your process stream. This is only going to be possible for certain kinds of streams, not for anything you need to keep absolutely pure, but by adding chromate solutions. And maybe this would be again into a recirculated water system where it's not going to be lost and poison the environment. We might promote passivation. If we had a stainless steel which was not quite as passive as we needed it to be, maybe we've chosen an alloy with too low a chromium percentage, then we could add chromate solutions to the stream passing over and causing corrosion of the stainless steel, and they would promote the formation of the passive layer. Again, that would be called an anode inhibitor. 5.4.3, this is an interesting one. We're talking about oxygen scavengers. So when we had this oxygen reaction which caused corrosion at a diffusion limited rate, a good way to stop that is by removing oxygen from solution. In chemical engineering, we have a zoo of ways of removing oxygen from solution. We could use inert gas sparging, bubble pure nitrogen through the liquid. We could use some sort of vacuum treatment to try and remove dissolved gases. Something that we do quite often in a recirculated water system is we would add chemical oxygen scavengers. Sodium sulfite, for example, will sponge up oxygen as per reaction 5.3. And another case, we might use reaction 5.4. This is, we might deliberately add hydrazine to a recirculated water system, and that will react with dissolved oxygen, forming dissolved nitrogen, which might come out of solution somewhere else, and water. So that hydrazine reaction is something that you might use in a stream where the more chemically harmless sodium sulfite was not acceptable. An example of this is in a coolant loop in a nuclear reactor. You might, in that sort of system, want to have absolutely no solid salt residue able to come out of solution, in which case you can't use sodium sulfite because the sodium sulfate and the sulfite could precipitate as solids that you don't want inside the system. Therefore, you might choose to use hydrazine. You'd obviously add a very dilute amount to your water stream. The hydrazine would react, absorbing oxygen and producing only water and nitrogen gas residue, which is not going to cause solid buildup inside the recirculated water loop. So there's quite a lot of considerations for inhibiting corrosion. Right, section 5.5 is talking about coatings as corrosion engineering solutions. As I said, conceptually, thermodynamic corrosion prevention and kinetic corrosion prevention are scientifically clean concepts which we can consider on their own, whereas coatings are a very practical engineering solution. This means they often do incorporate both thermodynamic methods. If, for example, a paint contains zinc particles, then it may provide some protection as a sacrificial anode. And the paint may also contain corrosion inhibitors, perhaps something like arsenic, but potentially less toxic, which cuts down the exchange current density or some other kinetic parameter which allows corrosion to happen. The main thing about coatings is, of course, that they provide a barrier which separates the vulnerable metal from its corrosive environment. So if we want to study coatings, therefore I'm going to leave you to read these comments in the notes, because many of these things about coatings are pretty straightforward and obvious, so you just need to read them. One is that the barrier lifetime needs to be known. Eventually they might fail because of erosion or mechanical abuse, or detach because of thermal cycling. Barrier lifetimes might often be known from measurements in a particular environment or from experience. Something specific to corrosion that you need to know about coatings is that you can have sometimes a partially detached coating actually as a problem, because it creates an environment very similar to the one which allows crevice corrosion to happen. If you have corrosion taking place in the same way as crevice corrosion quite severely but under a coating, then it's often called aggravated rusting. Another thing that you will have when you have this aggravated rusting is expanding corrosion products, which can exert high pressures, and those can further crack any coatings which are present, or it can even crack bolts in some systems. Okay, so further down this page 18, there are some comments about paints, which something to say about them. They're often slightly porous, so they may provide partial mass transport barrier, which somewhat slows down contact between the metal and the environment, but often they might decrease corrosion but not stop it completely. Hence why paints often do contain, say, zinc particles as a sacrificial anode or corrosion inhibitors. On the plus side, paints are very cheap, and they work very well if the conditions are only mildly corrosive. We say some things about plastics, rubber and glass coatings, all of which exist. They're more difficult to apply than paints, but they potentially provide resistance to all kinds of chemicals. If you're looking at Teflon or glass, they're often completely unreactive or inert in whatever chemicals you're using, you're containing. Slight issue is that they can be more fragile because you might be looking at layers of quite brittle materials in the case of glass. In the case of Teflon, you have some potential problems with detachment of the layers. We also have sometimes metallic coatings. Zinc is the one which there's a really good ability to apply it to all sorts of components, so that we now expect in the auto industry car parts surely should come coated in zinc if they're steel parts to protect them from corrosion. And this obviously provides both a mass transport barrier that stops the environment touching the steel. It also provides a sacrificial anode in the case that the coating gets scratched and there is some way that the steel could react with the environment. Then it won't, because the zinc will be a sacrificial anode. And another thing to say about zinc is that its kinetics for dissolution are quite slow. So even though you think it's a reactive metal and it's going to be lost quickly, its exchange current densities are low enough that it's lost fairly slowly, and it's a good coating. Other kinds of metal coatings, chrome, nickel, tin, these are very commonly used as well. These things are often passive, but they don't offer cathodic protection to the steel, because all of those things are, well, they're not substantially more reactive than the steel. In the case of chromium, they're not more reactive because they become passive. Okay, so we've talked there about coatings, and in section 5.6 we just talk about a couple more corrosion control methods. One of them is robust design. This means just if we're looking at a question where we're answering how many years is this thing going to last, we might be doing robust design so we have thick enough walls or thick enough metal that it's going to last even when we've allowed for some wastage rate because of active corrosion. That might be in some situations better than providing a corrosion protection system if we can't rely on the corrosion protection being observed and maintained. Of course, it does mean that we're looking at a finite lifetime. Alternatively, robust design also means things like prevent water pooling on some metal that can corrode, or it means if we have a process stream, filter out entrained solids or sands as early as possible if it's allowed to do so that they're not going to cause erosion corrosion. What else can we talk about? Environmental modification. So corrosion is chemistry. So one thing we can do to slow it down, in the same way we can slow down almost all chemistry, is to decrease the temperature. So if we have a process stream which at some point we're going to cool it down, or we don't mind if it's cool it down anyway, then we should cool it down as early as possible so that it's less corrosive to the metal downstream. We can do some things which are described as corrosion inhibition, changing the pH, or removing dissolved oxygen. In some cases, we might be able to do environment modification by removing water completely. This is something which effectively does have it happen in salt mines, in which you can be quite surprised that in your metal steps going down into the salt mine there's really bad rusting, but within the salt mine itself there's very little corrosion of even exposed metal objects. That's because the salt is such a good desiccant, it pulls so much water out of the air, there's no surface layer of moisture on the metal to allow electrochemical corrosion to even happen. Of course, you don't have to be in a salt mine for this to happen. Any dry air environment could be made deliberately dry so that this would be protective. Okay. Final thing to say, an important part of corrosion engineering is inspection and maintenance. I don't have a lot to say in this course on this subject because this course is more to do with the algebra and principles of corrosion. But these things of inspection and maintenance, these can be visual inspections for the amount of corrosion or as to whether localized corrosion has happened in a particular place. We could be looking at ultrasonic checks on the thickness of a reaction vessel wall. We could do X-ray measurements to look for parts which are becoming thin because of, say, pitting corrosion. We could also include in an ICCP system, we could include electrical monitoring so that we know if the system is continuing to apply the protective potential it should be and whether it's providing a sensible amount of current in order to provide this correction. Great. Okay, well, thank you everyone. I hope that you've enjoyed this course on corrosion, or at least that large parts of it have been useful for you. Please do comment, rate and subscribe to give me some cheer me up and give me some good reason to do some more lecture courses. For this lecture course, do make sure that you collect your copy of the PDF notes from the GitHub link in the video caption. Which, if you've got to this point in the course without having downloaded a copy and you were taking written notes, maybe that's something I'll mention at the start if I get the chance to do some more lecture courses. Hopefully I will on statistics as well as on a few other things, in which case I shall see you for them in the future.